Okay, hello everybody to today's ISGC seminar talk. Today's speaker is Dennis Rätzel. He finished his PhD in 2013 at the University of Potsdam and is currently at ZARM at the University of Bremen. And thank you very much, Dennis, for giving this talk. The stage is yours.
Okay, thank you very much, Torben, and thank you very much for the opportunity to speak here in your nice seminar, online seminar, international seminar. And yeah, so the topic of my talk today is perspectives of measuring the gravitational attraction of ultra-relativistic particle beams, a new testbed for gravitational theory at the Large Hadron Collider. And this is a bulky title, and the reason is that it's a collection of several articles together. It's kind of giving a bit of an overview. It has a certain focus on one specific article. That's maybe half of the talk, but then it's a real program to some extent towards these kind of experiments. So this is also there's the reason why there are so many people involved. In particular, Christian Pfeiffer, a colleague from the ZARM, and Daniel Braun and his former PhD student Felix Bengler at the University of Tübingen, Marta Maria Marchese and Stefan Nimrichter at the University of Siegen. And Marta Maria Marchese is now at the ISTA in Austria. There's Ronron Kai, Pascal Hermes, Chiara Makani, and Stefano Radelli from the CERN, and Henrik Ulbricht from the University of Southampton. That's all the institutions that are involved in that research project. Now, just as a motivation, usual tests of general relativity and modified gravity are done in certain systems or regimes, and those comprise, in particular, cosmology. Here on one side, then black holes. Then, of course, there is celestial mechanics, so in particular, the solar system tests of general relativity. And then there is gravitational waves. And of course, there are overlaps of those. For example, a lot of black hole physics is, of course, tested by gravitational waves and so on. So but that's usually what's used to test general relativity and modified gravity. However, all of those have one backdrop in common, or one disadvantage, and that is that these are uncontrolled setups. So in that case, the initial state and the whole setup is not controlled. It's not an experiment where you set up the state of the system that you're observing. You're just observing it. And of course, one would like to have also experiments where you really can prepare and measure. And that's the reason why we propose to look closer at ultra-relativistic particle beams. And so let's consider a situation like in that image here, we have ultra-relativistic particle that moves with close to the speed of light along a certain direction. So it's really in uniform motion, and it comes by a test particle. Now that test particle will be accelerated towards that source particle due to the gravitational field. Of course, the source particle will also be deflected. And then after that interaction, the test particle will have momentum transferred to it. So there's a momentum transfer, and so this is a standard scattering process, if you want. And these kind of scattering processes, of course, we could study on Earth in a situation where we have a source particle that is ultra-relativistic. And if you look at Einstein's equations, here on the left-hand side, we have the Einstein tensor and the metric tensor. That I mean, the metric tensor also is on the right, but here the Einstein tensor that depends on the metric tensor, and on the right-hand side we have the energy momentum tensor that contains the matter, and one can conclude from that equation directly that the energy momentum is the source of the gravitational field, and the gravitational field of ultra-relativistic matter must then be dominated by its momentum, and kinetic energy, because that contributes mostly to the energy momentum tensor. So that's essentially the definition of ultra-relativistic matter. And in the end, it's really a situation that is a completely new regime for lab tests of GR. A situation where the rest mass is not a significant contribution to the gravitational field. And one could, if one would be able to measure that effect, one would have the first measurement of the gravitational field of kinetic energy, for example. And yeah, so that would be already a gain by itself. So testing general relativity in a regime where it has not been tested by a direct test where you prepare and measure. And of course, a situation that could be interesting is the Large Hadron Collider, because there we have very ultra-relativistic particles. Here you see the Lorentz factor is 7 × 10⁻³ and yeah, so it's very close to the speed of light in that sense. Then this is a quite controlled setup. So we have these particles, protons in that case, moving on this 27-kilometer ring. And they run in circles with a fixed frequency and so on. So we could put test particles around the beamline and then see what happens to them. But of course, that's maybe not the ideal situation. One would not just have free-floating test particles, but one would use some sort of acceleration sensors. And one could now arrange them. I mean, one could also just use one, but of course, if you use more than one could improve the sensitivity. And then one would have a signal of this rotating gravitational source in the ultra-relativistic regime. And this proposal is part now of this DRD5 research collaboration on quantum sensors, where people want to develop quantum sensors for high energy physics, particle accelerators, and so on. And we contributed with that idea as a science case. And now the question, of course, is that experimentally accessible at all? And we did a study in 2022, or before 2022. We published that article in 2022 here in New Journal of Physics. And we looked into that question, particularly for the ultra-relativistic particles. We also looked at the gravitational field of light in that article, but we saw the clear advantages of the proton bunches at LHC. And if you could consider that situation now, so you have this particle, these bunches in the case of the LHC moving along the beamline. If you go close to the beamline, you can neglect that curvature of that trajectory. And we have bunches of a certain length. And if you're now close enough to the beamline, so this transverse distance rho, which we could also call an impact parameter, if that is much smaller than gamma times, so the Lorentz factor times the length of the bunches, then the acceleration towards the beamline of a test particle at rest, or an acceleration sensor at rest, or at least in a Newtonian regime of slow velocities, would look like that. So it's a very simple expression. You have 4 times the Newtonian gravitational constant times the pulse power divided by the speed of light to the 3rd power and the distance to the beamline. So it's very, very simple expression, and one can put in some numbers, particularly for the Large Hadron Collider, which has a certain circulating power that one can put in that equation. And then if we assume that we have one of these acceleration sensor it close to the beamline, let's say 1 millimeter from the beamline, then we find an average acceleration of 4 × 10⁻20 meters per square second. And that has to be compared, of course, to the smallest acceleration that has been measured to date, and that is of the order 10⁻14. So you see there is still a few orders of magnitude that one has to improve these kind of sensors. But of course, here we have a certain advantage, and that is that we have a periodically oscillating or pulsed signal, because we have these bunches, like displayed here by these red dots, and they have a certain distance from each other. So there is a certain frequency at which this acceleration signal appears. And also because all these bunches move on a circle, we have another frequency scale that is given by the circumference, essentially divided by the speed of light. So we can, and then there's a possibility also to move the beam back and forth. So we can get an oscillating signal, and then the sensors can be tuned onto that signal, and then one can use a method called phase locking, and then one can, in the end, improve the signal-to-noise ratio significantly. And that is the idea. That is one idea that one can use to improve the possibilities to measure that gravitational signal. Now we had, so this was just comparing the smallest acceleration that has been measured to date with that number here. But we had a look into specific systems that could be used in principle to measure the gravitational field of the Large Hadron Collider. And here in particular, we looked into this system. So this is a silica disk that is hanging from a silica string. And so that's an optomechanical pendulum with of 7 milligram mass. And it's an optical spring is used and a feedback cooling mechanism to cool it down. And this system is quite advanced and very precise for acceleration sensing, but it's still dominated by thermal noise. So that is still its limit. So there is space for improvement. But for that system, we get and we find that to measure the gravitational field of the LHC beam, there's still 7 orders of magnitude missing in sensitivity. Right. So that is also a problem that has to be overcome. And but we clarified, or we looked into the optimization of these sensors to clarify what would actually be needed to obtain a signal-to-noise ratio larger than 1. And then we found that if one would increase the mass to 33 milligram and change a few other parameters, in particular get the Q factor much higher and cool the temp, get a very low temperature, then one would in principle be able to get a signal-to-noise ratio larger than 1. So we clarified what is needed on the detector side. And then there's also other possibilities to improve the sensitivity. And one I already showed you. So one could put many detectors around the beamline and correlate the measurement. And then one may overcome the remaining orders of magnitude that way. But of course, if you put detectors and you just classically correlate them, then your signal-to-noise ratio will only improve with a square root of the number of detectors. That's also called the standard quantum limit. And there are possibilities to go beyond that, and that's so that's a possibility that we look into with Marta Maria Marchese, Stefan Nimmerichter, and Daniel Braun. So we look into the possibility to use these kind of optomechanical systems. And so here we have a input light that goes into these kind of optomechanical sensors. So this consists of a mechanical resonator here on that side, which is sensing the gravitational acceleration. And then there is another cavity mirror. And so there's light in that cavity mirror, cavity between these mirrors. And this light in the cavity is sensing the motion of that moving end mirror. And then the signal on the light travels with the light outside of the cavity and is reflected here at that polarizing beam splitter and then goes further into the next one. And if you now assume that there is a signal that has some temporal delay, an oscillating signal that has some temporal delay between these sensors, then you can imagine that one can time the propagation of the light here in the right way such that the signal is accumulating coherently. So it's adding up as a coherent phase shift. And then in the end, you get an improvement that doesn't scale like the square root of the number of detectors, but in principle could scale if there is no loss with a number of detectors. So there's a huge improvement. But of course, there is loss. So that is something that has to be taken into account, and that's work that that will be published soon. But anyway, that's also more on the detector side, on the sensor side. What is also interesting on the side of the LHC, we are collaborating with people from the CERN, Rongkong Kai, Pascal Hermes, Chiara Maccani, and Stefano Radelli, to figure out what other problems could appear. And in particular, they help us to look into the halo around the beam. So we have that beam that is, of course, not in practice, not one-dimensional. It has a halo, and that halo consists of protons as well. And these protons have a certain divergence. So there are always protons traveling into the surrounding systems, and in particular could hit the sensor, even if it is just a centimeter from the beamline. And if a one proton directly hits the sensor, we would get a momentum transfer that is about 10 to the 17 times larger than the gravitational momentum transfer due to a single bunch, not a single proton. So you see that is many orders of magnitude larger, and one has to avoid that completely. And for that, one has to use the collimation system to protect the sensor. And that's what we're studying here. And it seems that it is definitely possible to avoid these collisions, but one has to go to that distance of a centimeter from the beamline with the sensor. And we even put out some contribution to the European Strategy for Particle Physics, ESPP, recently in a collaboration with all these people that I mentioned before, and in particular also Hendrik Ulbricht, who works on acceleration sensors, levitated optomechanics, and these kind of things. We called it the path towards measuring the gravitational field of proton bunches at accelerators. So so we are working towards that goal, and we hope that at some point these kind of experiments will be done at the Large Hadron Collider, or in particular the follow-up accelerator, if it is built. But here, that was the first part of my talk, and now in the second part of my talk, I will focus more on what you can do beyond null tests of GR. Of course, it's already quite interesting by itself if one would measure the gravitational field of ultra-relativistic matter in a ground-based setup by itself, so confirming GR. But that is, of course, just a null test. The question is, what do other modified gravity theories predict, and what are you testing against? And in particular, one very simple and theory that came out to our mind is scalar-tensor theories. So that's a certain class of theories that is used, for example, to explain dark matter, the accelerated expansion of the universe, and inflation. So it comes up in different areas, and in cosmology in particular. And we wanted to see what is the prediction of scalar-tensor theories for the gravitational field of these ultra-relativistic particle beams. And so we started with these Bergman-Wagoner theories that are defined through this action that you see here. So we have here that the Einstein-Hilbert action is added, so there is a scalar field added to it. So here you see that scalar field psi in front of the Riemann scalar, the curvature scalar, and then you have second derivative. There's the first derivative parts here that give rise then to the Klein-Gordon equation, usually here with a few factors, and then the potential. So that's the action that one starts with, and this is fairly general. There are some conditions on this function omega psi that appears here in front of the kinematical part. And then there is a potential V. For the potential V, we have also a condition. But otherwise, this is fairly general and covers a lot of these scalar-tensor theories. And in particular, it contains the scalar-tensor representation of f of r theories. So we cover not just scalar-tensor theories, but also f of r theories with that. And now, the first thing that we need to do, of course, is to linearize the theory, because we are working in a weak gravity regime, and there's no point in doing the full theory. So we expand the metric into a background metric. We use the flat Minkowski metric plus some metric perturbation, and we do the same with the scalar field. So there's this background scalar field psi0 and perturbation psi1. Then we use generalized version of the harmonic gauge. So you see here that first part is the usual harmonic gauge from linearized gravity, and then there is a term added that comes from the linearized part of the scalar field. And then we have also a trace reverse shifted metric perturbation, like what you usually do to obtain the linearized Einstein equations in a easy form. Here, there's also another term coming from the scalar field appearing here. And then we use a few assumptions about the background scalar field. It should not vanish. It has vanishing derivatives. And when we assume that the potential is 0 and its first derivative as well, so only the second derivative of the potential appears here. And if we do that, then the equations actually become quite simple. So you see this is the set of equations that we get down here. So this is the linearized Einstein equations, very similar to the linearized Einstein equations that most of you will be familiar with. And then down here we have a Klein-Gordon equation with a source term that is the trace of the energy momentum tensor. And this part here, this mass in front here that is defined through the second derivative of the potential. And we call this the effective mass of the scalar field. And now one can solve these equations for a relativistic point particle source. So we assume this energy momentum tensor here. So it's really a point particle moving with a fixed velocity v along the z direction. It has a given energy and has a fixed velocity, and that defines the energy momentum tensor. And now there are two possibilities to solve these linearized equations that I've shown you before. So first is one can just use the method of retarded potentials to solve the equations. Another possibility is to look into the rest frame of this point particle and then solve the equations there and then Lorentz transform. So that leads to the same results, and the results are given down here. So you see this is the solution for the scalar field in the first line, and then the second line we have here the metric perturbation, which can be split into two terms. One is proportional to this k function here, and another one proportional to the h function here, that's again proportional to the k function. The important thing to notice is that if you for the moment neglect that these exponential terms here, or exponential factors, then what you see here is a boosted Newtonian potential, essentially, very similar to the boosted Coulomb potential. So it's a central potential 1 over r that is boosted to the lab frame. And you see the same here for the metric perturbation. You also, in the first term, in this k function, you see the same factor. What is additional to the JR case is this exponential decay here, and that with the length scale given by the inverse of this effective mass that appears in the scalar field. So you see this is kind of a Yukawa potential in both cases for psi1 and h mu nu, and that's of course what you can expect if you go to the rest frame of that particle, then you would find some Yukawa type modification of the Newtonian force law, and that will come up later again. But now we can look into the acceleration of a test particle in the vicinity of a point particle that moves like that, so in that gravitational field. And for that, of course, we look into the geodesic equation that you see here. So the acceleration is given to leading order so if we assume that the test particle is at rest, or at least only slowly moving, then we find that the leading order contribution is that expression here. So it's the spatial derivative of the h00 component, and then there is a time derivative of the h0j component, where j and I are now running from 1 to 3. So that's the spatial components, and t is the time component. And 0 is the CT component, so the temporal component. And now if we use the expression that we had before, then we find the acceleration down here. So you see, if we assume that, so if we just look into the transverse direction, so now k is running from it's only the transverse components, so it's just x and y, 1 and 2, and then you see if in that case this transverse acceleration, we don't get a term through the time derivative. You just need to look into the spatial derivative of h00, and then that is what we find down here. So now we have something very similar to a boosted Newtonian force, Newtonian gravitational acceleration, but there is, of course, a contribution due to the kinetic energy of the particle. That's this term that comes with a gamma square here. And then there is an exponentially decaying part that comes through the scalar field. And what is, of course, important here is that in these expressions, the theory parameters, so the background field value, this omega 0, which is the function omega that appeared in the action, evaluated at psi 0, and the effective mass appear. And now we can just look into the acceleration. Here I have a plot for specific values of these parameters. So I defined that combination of parameters up here, such that we just have that one parameter that we have to fix, and then just look into renormalized accelerations here. And we see that, and the only length scale that appears is given by the inverse mass of the scalar field. So we can just use this for normalizing the axis. And then you see, if I do that, on the left-hand side, you have the GR case, so sigma equals 0. And on the right-hand side, we have the case where sigma equals 10 to the 2. And you see that if you are far away from the source, then they coincide. There is no visible difference. But if you go closer, then they deviate. And that's exactly what you expect from something like a Yukawa type potential. And this, of course, due to this exponential decay that at large distances, you don't find a difference between the two. So, but now a bit of a disclaimer. So this sigma equals 10 to the 2, that is very close to the parameter value where omega 0 is minus 3/2, and that is where the theory is loses its validity or consistency, because there are terms that diverge. So, and that is not a very natural value for that parameter, but this I've chosen that here to make the visualization easier and possible to compare this visually. But anyways, what you want to look into is, of course, not just the acceleration, but you want to be sure that this is not just a coordinate effect, but really a physical effect. And for that, you have to look into the geodesic deviation. So the differential acceleration between two infinitesimally neighboring geodesics. So there is here you see these two geodesics. Then there is a distance vector s that connects the two geodesics. And now the question is, how does that evolve over time? And here again, that's the geodesic deviation, geodesic equation. And down here you see the transverse geodesic deviation, how it evolves. So the second derivative of that deviation vector. And in the transverse direction, so let's assume that situation here, you have now two test particles. And the question is here, what is the differential acceleration of these two test particles at rest in the direction of the transverse to the beamline? And they are oriented in a distance that is also transverse to the beamline. And then you see that this expression for this change of the time derivative, second time derivative, that geodesic deviation is given by the gradient of the acceleration, but there's also another term appearing, and that is the second derivative of that h function that you've seen here. So that's this h function over here. But if we now assume that we are looking into a sensor or look into our test particles only after the interactions, we are looking into the integrated signal. So let's assume we are integrating the acceleration over the interaction time. from -infinity to infinity, like in a scattering process, and really just look at the momentum transfer on the test particles, then this term will not contribute because it is a time derivative. So in the end, and the h vanishes at infinity. Now, we found that the time integral over the longitudinal geodesic, and we also found that the time integral over the longitudinal geodesic deviation, so here this is the transverse geodesic deviation, but the time integral over the longitudinal geodesic deviation completely vanishes. So in the end, we can conclude that the only important contribution is the transverse acceleration that I've shown you here. So that's really the significant effect on the test particle. And in particular, we look into the momentum transfer. And this is the expression for the momentum transfer. So it looks a bit easier now than the acceleration. You see, again, this is just now in that case 1 over distance. So an acceleration that is proportional, or a momentum transfer that's proportional to 1 over distance. Here you have two terms again. One is contains the Lorentz factor, so that is related to the kinetic energy of the test particle. And here this is a Bessel function, so also that one at large distances will decay exponentially. So that comes from the exponentially decaying term that was a result of the presence of the scalar field. Now we can look into this transverse momentum transfer for different values of this effective parameter sigma. And you see for sigma 0, sigma 1, sigma 10 equal 10, and sigma equal 10 to the 2, we have different behaviors at close distances, but at large distances, all of them behave similar to GR. So it's again a situation as before. And so we see deviations at close distances. And now we have to ask the question: how can we compare this? And in particular, we can look into how can we test that in practice? And for that, we notice that there's not just this dependence on distance. So it's not just that this scalar field term decays if we go to large distances, but because of that gamma factor appearing here in the denominator, we see that actually this term in the back here is, and the gamma factor here appearing as a gamma square in the numerator, we see that this second term that we said is due to the scalar field is actually suppressed in the ultra-relativistic regime. So if gamma is becoming very large, that term contributes less. So that means that we can test this model by comparing a measurement in the non-relativistic regime with something that is a test in the ultra-relativistic regime. And so we call this an auxiliary measurement in the Newtonian regime. But that, of course, there's some possibility that directly comes to mind, and that is the measurement of the gravitational constant, because that is usually almost always done for the high precision measurements, at least in the Newtonian regime, and also at close distances. So we consider an auxiliary measurement of the gravitational constant in the non-relativistic regime. And if we interpret that in the GR framework, then we expect an acceleration that has that form with a distance dependence given by 1 over r0 square. So the distance of measurement. So now, so that is the gravitational constant, kappa r0 here, that is then measured in an experiment at a certain length range, in a certain length regime. And if we compare this with a scalar-tensor theory, the predictions of scalar-tensor theory at the same distance, then we see that that has a different distance dependence. And here in the scalar-tensor theory, of course, the bare gravitational constant, kappa, of the scalar-tensor theory appears. And we can now use that measured acceleration and its interpretation in the GR framework to get a value for the bare gravitational constant, and it's given down here. So by just inverting that equation, we get now this bare gravitational constant that we can then use to predict a measurement in the ultra-relativistic regime, and then compare that to a potential measurement that would be done, for example, with the LHC. And here that's a plot of the momentum transfer, the relative momentum transfer difference for the GR case and the scalar tensor theory case for specific values of these parameters of the scalar tensor theory. Here I use the notions that are common in Yukawa type, or in this Yukawa theory, the phenomenological framework of Yukawa potentials. So the alpha is the amplitude of the Yukawa potential, and lambda is this has the length scale on which it exponentially decays, and they correspond to, in our case, to the in the scalar tensor theory case, to 1/3 plus 2 omega 0, and lambda to the inverse of this effective mass of the scalar field. And if you pick these values here, 10 to the minus 3 and 10 to the 2 meters for lambda, these have not been excluded experimentally. And in particular, here we see that 10 to the 2 meters, so hundreds of meters, that's much larger than the length scale on which the Newtonian gravitational constant is usually measured, or that is measured in all high precision experiments. They are performed at centimeter or meter scale. So this is so we have an auxiliary measurement that is performed in a close distance Newtonian regime. And then we compare with a result here from the scalar tensor theory in the ultra-relativistic regime, and we see that if one goes into the ultra-relativistic regime, let's say 2 or 2.5 gamma equal 2 or 2.5, then we see that there is a deviation of this relative momentum transfer difference that is from 10 to the minus 4 to 10 to the minus 3. So already significant if one would be able to go beyond measuring just the gravitational field of the LHC beam, but measuring it with a high precision. And that is, of course, something that is then also more for the future. But we see that there is this difference. So in principle, one can test scalar tensor theories at the LHC. And of course, one could go beyond that. We didn't yet, but in the future we might, and look at other modified gravity theories. But now I would just like to summarize. So general relativity predicts that the gravitational field of ultra-relativistic particle beams is dominated by kinetic energy. And the main results of our research that I presented to you is that we did a feasibility study for optomechanical sensors. And we found that measurements of the gravitational field of the LHC beam, or the follow-up accelerator, may become possible in the future. There's an advantage of coherently coupling sensors. In particular, one can go into some quantum metrology regime and use some advantage there. And we studied in more detail modifications of the gravitational field of the LHC beam of ultra-relativistic particle beams based on scalar tensor and f of r theories. And we found that tests of modified gravity are in principle possible. Now, there are these articles that are there for further reading, if you like, everything online. More is to follow. And I'm here for your questions, if you have some.
Thank you, Dennis, for this really nice talk. Are there any questions?
Can I ask a question?
Yeah,
Of course.
please.
Do you think it would ever be possible to confirm with measurements that a light from a light bulb is capable of inducing a gravitational field? If we ever have the measurements sensitive enough to confirm that.
Do I have a slide on that? Not from a light bulb.
Not from a light bulb.
From a laser beam. So here, if you look at that situation, so we in the same paper that we looked into, where we looked into the gravitational field of the Large Hadron Collider, we also looked into the gravitational field of laser pulses. I did some articles before that on lasers, just laser pulses that come by. But here we looked into something where a cavity is present to enhance the intensity. So here, for example, one could have a laser pulse moving back and forth between the cavity mirrors, or one just pumps a cavity periodically with a light and enhances the intensity. And of course, then there's a natural boundary to that, and that is at some point the mirrors will just start melting. So, and if you go, if you calculate what is the bound given by that, then you see that you can go to high pulse powers, but the important thing is the circulating power, this average power that I've shown you that goes into the acceleration. So I had that expression for the gravitational acceleration in the beginning, if you remember that one here. So you have the power here. So that's in the end, what is important for the average acceleration, it's the average, not the pulse power. So the circulating power of the circulating average power of the of that system here. And you see if you compare the numbers, so the best you can hope for in the case of a laser cavity is 10 to the 11 watts, but the LHC already provides 3.8 times 10 to the 12 watts. But in terms of focus, I mean, the LHC can be focused much stronger to 16 millimeters, but still you cannot go to that distance. You can go in principle to a millimeter distance, but as I told you before, there's this halo and so on, so one shouldn't go to a millimeter, should go to a centimeter. And the same for so then in some sense they are similar, at least from that perspective. So one can go to a distance of, let's say, a millimeter, also close to this laser beam, because also that one can be focused strongly. And then if one is able to measure the LHC beam, then it's just about 1 order of magnitude to measure also the gravitational field of that laser beam here. So I would say it's possible at some point, but the disadvantage here is that in that case of the LHC beam, we said we can put a lot of detectors around the beamline, around the whole LHC circular ring, but there is no chance to put more than, maybe one could arrange detectors like azimutally around the beam waist of that detector, but there is not much space to put many detectors here. So that's a bit of a disadvantage for the laser cavity case. But in principle, there's a possibility, and one can think about other ideas. And there's a lot of interesting stuff around about that, and also what gravitational waves are produced by laser pulses and these kind of things, which is then even more unmeasurable. And we studied also the effect of circular polarization of light. Then you get frame dragging and all these kind of interesting effects in the vicinity of laser beams as well, and rotation of polarization of other light and so on. And that's quite interesting phenomenology that is, of course, so remote that this will not be measured in our lifetime, I'm sure. But maybe just the Newtonian, or this Newtonian acceleration, gravitational acceleration.
Okay. So it would require more advanced technology to confirm that the light from a light bulb
the light
can
from the
induce a
light bulb, yes.
gravitational flow.
Yes, the light from the light bulb is just not enough energy, yes. It's
Okay.
yes.
Okay, thank you.
You're welcome. Thanks for your question.
You're welcome.
Any other questions? If not, maybe I can ask one. I mean, we have also theories of massive gravity. Did you investigate if there might be an effect due to that on the things you want to measure?
I am not familiar with them. I guess one could just, I mean, we didn't to answer the first question, but so I guess the point is that if you start with any action here, then using the linear polarization procedure, you should arrive at some modification. And all of these theories are, of course, interesting to study and see what happens. I mean, because of that distance dependence in the scalar-tensor theory that is exponential, I was actually not so optimistic in that case. So I can imagine that there are more interesting modifications of GR for the ultra-relativistic case, actually, where the velocity dependence is much different, and there's much, yeah, I think there could be more interesting cases to study. And maybe this massive gravity case is something. So one would need to look into it in detail. But I'm not so familiar with these kind of theories.
Thank you. Are there other questions?
So this is also for advertising for that. So if you like that idea, ultra-relativistic matter, and you are working on modified gravity, why not on a specific modified gravity theory class? Why not look into this and derive the modifications? And yeah, I think that could be interesting.
Yeah. If there are no further questions, I suggest to end the official part of the talk here. Thank you very much again, Dennis.
Is there any way I could ask? And is there any way I could ask any unrelated questions to specifically what we're talking about, but it is related to inducing a gravitational field and contributing to the stress energy momentum tensor?
Okay. Say it again. That was the question, or?
Okay, so yeah, so say if we had an entity whose disturbances in its incident waves were to perform certain transcending, perhaps we could call it, of the laws of physics, would that indicate that it's not contributing to the stress energy momentum tensor? For example, if the disturbances in this incident waves, okay, were to exert a force on ions without scattering, refraction, reflection, or absorption by the ions, if it could reverse the disturbances in this incident wave, could reverse its direction, okay, without an even change into other directions, without a net external force being exerted on those incident waves. Okay, so it would transcend, it'd be essentially transcending all three of Newton's laws of motion. And if it could, this entity, the energy in this entity could not be transformed into heat, for example, converted into heat or other forms of energy, mechanical, chemical energy. And for example, if you could transfer energy momentum to this entity without increasing the amplitude in the incident waves or increasing the conduction velocity of it, and if this entity could change its frequency of oscillations, so increase its frequency of oscillations without an input of energy, and it could decrease its frequency of oscillations without an output of energy, would this entity be essentially not contributing to the stress energy momentum tensor and therefore not be capable of inducing a gravitational field? Would that be enough if it was performing these types of phenomena? Would that be enough to indicate to us that it's not contributing to the stress energy momentum tensor and therefore not inducing a gravitational field?
I would say at least you are not forced in that case to include it into the energy momentum tensor, right? So if it would be the other way, so it's not really answering your question, but I would say it's more like it can only confirm the other direction to some extent. I would say it's if it behaves in the opposite way than what you just said. So if it behaves normally, then it should also contribute. But the other way around, I can't say if that is enough.
So it's not behaving normally, obviously.
Yes, no, of course. But as I said, so if it's there's the divergence of the stress energy tensor has to vanish, yeah, in GR at least, and then if you have all these contributions, all transformations of energies into different forms of energy have to be kind of involved. Otherwise, you violate that condition.
Yeah, it cannot be transformed into other forms of energy, like heat energy,
Yes.
And
Yeah, if
and
it
so
cannot
that
be transformed in any way, then it, as I said, so you are not forced by the mathematical properties of GR to include it into the stress energy tensor, I would say. But
yeah, and it could move immediately upon interaction with ions, for example. It would cause it to move at a constant speed, constant velocity. So no acceleration, no you know um, initial upon initial exerting a force on the ion, it won't cause it to accelerate, and then due to friction of the ion moving through a certain medium, that friction from that medium is not going to cause it to move at a constant velocity. Instead, the constant speed of the ion is wholly accounted by the disturbances and this incident waves of this entity to cause it to move at a constant speed. That also would indicate that it's not contributing to the stress energy momentum tensor too, wouldn't it?
yeah, I'm not so sure about that. So I cannot answer
I'm
that
not sure
question.
about that. Okay, but if I ever wanted to email you, the paper Perspectives of Measuring Gravitational Effects of Laser Light and Particle Beams, the email that's associated with that paper, I could email you if I have any questions in the future at that email address. Dennis.Rätzel at szarm.uni-bremen.de.
That one down here, yeah.
That's a good email address.
Yes, that works.
Okay, so if I ever need, do you see my name on the screen there?
Yes.
Okay, Kenneth Woffenden.
Mm-hmm.
Okay, perfect. So the Ken Woffenden. Okay, so if I ever need to email you in the future, I could email you from. I'm a student at Concordia University in Montreal, Canada.
Ah, yeah. Okay.
So I would email you from my Concordia email address. Okay.
I see. Okay.
Oh, okay, perfect. All right. Thank you very much. Especially, thank you for answering my question. Thank you very much for your lecture. It was very interesting.
Yeah, thanks. Thanks for your questions.
Okay, thank you. Have a good day.
Okay. Then I would say last chance for questions. Okay, there's now one in the chat. Thank you very much for the nice talk. Have you considered sources other than LHC, say the strong current acceleration produced by the undulator? Would it be strong enough, or would the source be better designed specifically for gravitational wave production?
Yeah, that's of course a good question. We didn't look into that. But of course, that's something that one could consider because, yeah, you're right. In that case, here we are not talking about gravitational waves, right? So this is just that is just the gravitational near field, if you want, right? So it's just the boosted near field of a particle at rest. So it's not decoupled from the source. It's if you want to look at it from yeah, so it's really just it's not the propagating degrees of freedom of gravity that are involved in here in that. So the other case where you have the ondulators, then of course you have accelerations, and I guess you can also get something like a quadrupole moment, and then you might get emission of gravitational waves. And I know that people at CERN, so there is some people at CERN that look into that. I can't tell you names, but can look that up. There was even a workshop on that last year or so where people met and discussed these kind of questions. So what are the gravitational waves that are emitted at these accelerators, and maybe they looked also into the ondulators and their emissions and so on. I hope that answers the question.
From the chat. Are there other questions? If not, then I would suggest now we finally end the talk, at least the official part. Thank you very much, Dennis, for the nice talk again.
Yeah, thanks again for the invitation.